All right, so this is section 2.1, rates of change and tangent lines to the curves. Okay, we are going to start with this. So I want to start with the average speed. Actually, this in this section we are going to see these tangent lines. Tangent lines are actually rates of change, and tangent lines are the basics of calculus. Actually, how you can this calculus evolved by some main questions, which actually led mathematicians to come up with these terms, tangent lines and rates of change, etc. So just a sec, let me turn this off. Just one sec. Okay, so so it's an important section. That's what I want you to understand. So average speed we are going to talk about. You guys know what a speed is, what a velocity is. Velocity is a speed plus the direction. If you remember from physics class or science class that you had in high school. And now we are going to average that speed. Okay, we are going to take the average of it. But how would you do that? So let's say there's an object that's traveling. Okay, that's an object that's traveling. Maybe I can write some stuff here. Just a sec. Okay. Yeah, there's an object traveling, and let's say f of t is the distance traveled at time t. Okay, it's going to show, for example, when t is equal to 1, f of 1 is going to show how far did the object traveled. Okay, it's going to show you the distance. For example, f of 0 is going to be equal to 0 because no distance is traveled at that time. It's time is equal to 0. Nothing moved. Okay, so so an object is traveling along a line, and it's gonna travel from time t is equal to t1 to time t is equal to t2, and then we can easily figure out the distance traveled if you take the difference between f of t2 minus f of t1, because f of t2 is the distance it traveled at time t2, and f of t1 is the distance traveled at time t1. If you take the difference, it's going to be the distance traveled. Okay, and then t2 minus t1 is going to be the time that has passed during that travel, during that trip. Okay, so if you take the ratio of the two, okay, if you take the ratio of the two, the average speed of that object, whatever that object is. Okay, so probably I don't need it to write anything here, so I'm going to just delete that. So this is an important definition, because it's going to take us to the definition of finding the instantaneous velocity of an object. Okay, the instantaneous speed of an object. What do I mean by that? So usually we are interested in the speed of an object at a certain time, but we may not have that information. Okay, but if you are given some, if you know the distance function, and if you know the time that are given, then we can actually get a close value to the instantaneous time. The time at the instantaneous velocity, which means it's the velocity at that certain time. Okay, we can find it out. So therefore, this average velocity definition, average speed definition is very important. Okay, now therefore I'm going to tell you actually how to get to that instantaneous speed. Onlookers, we want to get that speed at a certain time. For example, at time t is equal to 5, at time t is equal to 6. What is the speed of that object? Okay, we are interested in that. And now I'm going to teach you how to get to that. Okay, so what you do is we have such tables, a table that we come up. What is this table? Actually, this table is going to give us list of average speeds, okay, over an interval, okay, of length h. And we start maybe at time t is equal to 0, or at time t is equal to 1, at time t is equal to 2, okay? So it's going to give us that table. This table is going to give us that. So So let's say if the length of the time interval, we call it h. If the length of the time interval is just 1, then we use the velocity function. Let me see whether this comes from the example. Just a sec. Yeah, because this formula is the distance formula. Okay, let me write the distance formula actually to you, because it doesn't say right here. I need to add that here. Okay. Okay, let's see. Okay, in this example, okay, table 2 that we have. Let me try to fix it here. I mean, fit it here actually. Okay, here we are talking about the distance function. Just a sec. Okay, f of t we are interested in, and f of t is actually 16t squared. Okay, 16t squared. This is our distance function. Okay, and this is given. Okay, this is given, and this is a given, and this is given. This is given. Okay, and then okay, and then we are also given the time interval. The time interval is going to, just a sec, length of time interval. Okay, and then the starting point. Okay, let's just look at this part, this table, and let's say we start at time t is equal to t naught. I mean, this little t naught. Little t naught is the initial time that we start. So we start at time t is equal to 1. Okay, and then the object is traveling with this distance function. Okay, and then the average speed is what? The average speed is written here. It is delta y over delta t, which is f of t naught plus h minus f of t naught over h. Okay, so this is the average speed. Okay, average speed is, as you would see, this is the ratio of, if I can write it here, f of t naught. T naught is the initial. They call it t naught. The reason is they want to change the t naught. They want to start at time t is equal to 1 in the table, and they want to start at time t0 is equal to 2. So that's why they want to just call it t naught. Okay, and then so this is going to be the distance that it traveled after t naught plus h, length interval we add, minus, okay, minus f of t naught. Okay, controls the f of t naught. I'm going to write it like that. Maybe I should make it a little bit bigger. Okay, all right, I'm going to put this in bracket because I'm going to write the ratio of the number, ratio of these two terms over, okay, this is over, the time interval it passes, right? T1, T2 minus T1 you can consider, like we had it before. But in this case, it says, let's call it H. H is the time interval. Okay, H is the time interval. Time interval. Okay? Therefore, we just take the ratio over H. Okay, so this is going to give us the average speed in this case. T naught plus H is the next time that we calculate the distance, and T naught is the initial time that it travels, the initial time that it starts moving. Okay, so this distance, or this is going to be this is distance traveled, total distance traveled in h seconds or h minutes over h minutes or h seconds, whatever the unit is, passed. Okay, this is the average. Okay, and then why this is the formula that we have here, and then we just build this table. So why do we build that? Okay, we are trying to, okay, consider this interval. I want to I want to draw it. I want to draw a line. Okay, you can consider this time interval as like this. Look, I want to draw that here. Okay, this is the time interval, consider. Okay, and at the beginning we have the time t naught here, t naught, and then time passes, and we come to here t naught plus h. Okay, let me write this like that. This is t is equal to t naught, and then this is the the object traveled here, and then it's going to go up until, let me copy paste to make it faster. Okay, this. Okay, this is where it is going to stop, say. Okay, and I'm interested in finding the instantaneous. Okay, we want to find. Okay, our goal eventually our goal is find. Okay, find the instantaneous speed. Instant speed, you can say. Okay, instant speed. Excuse me. Just a sec. Just one sec. Okay, I'm with you right now. So this is the object is traveling from here to here, and we are. It's going to start at time t is equal to t naught, and it's going to go until time is equal to t naught plus h. So we have h seconds or minutes pass, or h hours pass. We want to find an instantaneous speed. Instant speed at time t is equal to. I mean, not that. Copy paste. Okay, we want to find the instantaneous speed at t is equal to t naught. That's the problem that we want to actually figure out in this class. Okay, and we are going to use the average speed to get to that. And the limit idea comes from here too. Okay, and I'm going to show you the relationship that the limits, because our chapter's title is limits and continuity, right? So the limits has a relationship between these things that we are discussing right now. Okay, everything came from the real life because people wanted to find the instantaneous speed, and then they looked for answers, and then they came up with this limit notion. Okay, and limit notion helped us to find the instantaneous speed. Okay, that's where everything comes from. Okay, the way we are going to do the instantaneous speed at time t, not on an interval h, okay, when we are given. So we are going to, and say we have this distance function as well. We are going to calculate this average speed for time intervals that are getting smaller and smaller. Okay, solution, maybe I should write it here, write it in words. Okay, solution. Okay, let's see. We will calculate, let me write this like that. We will calculate average speed in an interval h, where h gets smaller and smaller, so that it is almost zero. Okay, so the time interval this time interval that we are saying here, if this time interval is just gets closer and closer when we calculate the average speed, then we are going to get closer and closer to the exact value of the speed at time t is equal to t naught. Okay, that's the idea. Okay, that's why we have this table. Just a sec. We have this table here. So for example, this time interval is getting smaller and smaller. Do you see that? First, our time interval is h, and 1, it's big. And then 0.1, it's smaller than 1. 0.001, it's smaller. So our interval is getting smaller and smaller here. Do you see that? And then each time we calculate the average speed by using our distance function and using this formula. and see it is getting smaller and smaller. It's first 48 mile per hour, let's say, 33.6 mile per hour, and then it's 32 mile per hour. Okay, but assuming that we want to find the instant velocity at time t is equal to 1. Okay, and we are going to say, by looking at this table, we are going to say, as we get close to the T naught value, as you would see here, we are going to get the 32. Okay, smaller and smaller. Okay, so from the table, we get that instantaneous speed, the instantaneous speed at time t is equal to T naught is 32 something. 32 what? Let's recall it. Okay, is close to 32. Okay, it's close to 32. Okay, so mile per hour, let's say miles per hour. Okay, I just put the unit as well. Okay, so this is how we do it. But if the question was find the instantaneous point, the instantaneous speed, I'm going to change the question. The goal, let's change the goal to this. Okay, maybe I should, okay, make a correction here, just a sec. At time t is equal to T naught, which is 1. Let's make it 1. Okay, if you like, let's write it like that. Okay, instantaneous. Okay, so the spelling is right. Okay, so t, okay, we should write it like this here. At time t naught is equal to 1. Okay, and then next we want to find the instantaneous speed at time t naught is equal to 2. So how about the speed of the object at 2? After 2 hours, what's the speed, let's say? Okay, so we are going to do the same. We are going to build a table like we did, and we are going to get closer and closer to, we are going to make the interval smaller and smaller so that we are approaching to 2. Okay, and then, okay, let me write that. Then in this case, if you do the calculation right, okay, like in the table, look at the table. I'm going to go back to the table. See, average speed over the interval of length h. So the h could be 1, 0, 1, 0, 0, 1, blah, blah. And the corresponding average speed is going down and down. And it's going to get close to 64. So this is going to tell me that actually the object that's traveling at time t is equal to 2 is going to be around 64 mile per hour. Okay? So let's write it down. Where's our, yeah, it's here. Sorry about that. Okay, so in this case, it's 64 miles, okay, per hour. So this being twice of the other is just a coincidence, okay? Okay, it is related to the function, actually. It's related to the distance function, okay? It's not going to be always like that, okay? Since time t is equal to 2 is twice of time t is equal to 1, then we get 32 times 2 is 64. That's not the case. Okay, it's just a coincidence. It is related to the distance function. Okay, so I want to know if you have any questions. Can you follow me? Am I too fast? Like, if I'm fast, I can slow it a little bit down. Can you understand my English? I know this is your first year, so it's okay that you may not. But let me know. Yeah, please comment on this. We have 16 minutes. But if you cannot follow me, that's a big problem. Okay, are you doing well?
Yes, teacher. But there is just one problem.
What's that?
Sometimes when you are explaining the solution or writing a question, the screen freezes and the letters comes later from your speech.
Okay, yeah, there's
Maybe
still
it's
a
just
delay.
because of me. I don't know.
No. If you get a little bit slower, it will be better, says Selçuk. Yeah. Yeah, there's a delay still. You are experiencing it. It's the internet, I believe. I mean, it could be either on your side or it could be on my side. We don't know. But there's a delay. That's true. Yeah. But I think in the recordings, you're not seeing that, right? In the recordings, they should be okay.
Yes, probably.
Okay. So as far as I went over the recordings, they are okay. They are synchronized. But here we have a little bit problem. Yeah. Actually, yesterday it was worse because we had like 10 seconds delay. I don't know how many seconds delay right now, but I think definitely less. Okay. So let's move on. Okay. So next thing we are going to be talking about similar. Okay, just a sec. Just one sec. Okay, so I'm back with you. Here, so we talk about the average rate of change. Now, is this a new definition? Not at all, okay? So what we had talked about, average speed, is coming from the real life, okay? It comes from the real life, real experience. Then mathematicians, they just say, can we just rename it in a way that we can apply it in other situations? Because there are some other situations that are coming from real life. They may not call average velocity, but they have a similar situation. So this average rate of change is a terminology to all such situations that are coming from real life, okay? So from now on, average rate of change of y is equal to f of x with respect to x over the interval x1, x2 is delta y over delta x, which is actually, in this case, again, f of x2 minus f of x1 over x2 minus x1. Here, just a sec. Okay, I'm back with you again. Here, the average rate of change of y is equal to f of x with respect to x over the interval. Now, if you remember, in the previous slide for the average speed, instead of x, we had the time, t, right? And here, we just generalized this x may represent a time if we use for velocity, speed, etc., or it may mean something else, okay? So we have this x variable here instead of t, time variable here, okay? F of x2 minus f of x1 over x2 minus x1, okay? Again, similar thing, we use h because h is used for the time interval. So x1 plus h is going to be the next x, I can say, like x2, okay? So and x1 is x1, okay, over h. And of course, h is never ever 0. Okay, so this is a generalized definition of what we had seen, average velocity. Okay, you should just consider it that way. Now we want to see it pictorially. Pictorially, what does it mean? Okay, what is delta y over delta x pictorially? Okay, let's consider our f function has this blue graph. Okay, so delta y over delta x is actually, you can consider this as f of x2 minus f of x1. You see that, right? This is f of x2, this distance, and this distance is f of x1. If you take the difference between the two, then you get the delta y. Okay? And then we have the delta x, which is h, which is the difference between x2 and x1. Okay, so delta y over delta x is what this means. Actually, delta y over delta x is something that is known. It is the slope of something, slope of a line. But in this case, it's the slope of the secant line. Let me tell you a secant line. What's the secant line means? Okay, secant line, let me write it here. Secant line is a, okay, secant line can be formed by connecting 2 points on the graph. Okay, so this is called the secant line. Okay, we have also the tangent line. Okay, secant line can be formed by connecting 2 points on the graph, but on the other hand, tangent line that we are going to see, tangent line is a line intersecting the graph at 1 point, intersecting the graph of f of x at 1 point, at 1 point. Okay, that's the difference between the secant line and tangent line. Okay, on the graph, let's write it of f of x here. On the graph of here f of x, because we are talking about the same f of x here. Okay, so in other words, we are going to say then rate of change. Okay, note, we are going to write the note, then the rate of change, okay, here, let's go back to the previous page. The average rate of change of f with respect to the, if I can copy this page, no, I can't. The average rate of change of y, f of x with respect to x over the interval is, okay, the average rate of f of x, f of x, okay, the average rate of f of x, which is data y over data x, okay, which is data y over data x, is the slope of the secant line. Okay, we have a secant line here, so it's the slope of that, right? Data y over data x is the slope of secant line. So actually, the secant line is important as much as tangent line. Okay, so we should write it down. Okay, secant line is important. This is note 1, because sometimes students don't care about the secant line, but only they care about the tangent line. Okay, secant lines are as important as tangent lines. Okay, tangent lines. Okay, so we should pay attention to secant lines as well. You can also consider, if we didn't have secant lines, we wouldn't have tangent lines. That's that much important. Okay, you wouldn't be able to get to tangent lines if we didn't have secant lines. So it is important. Please keep this in mind. Okay, so that's what we got here. Okay, let's continue. Let's consider a circle where let's consider a circle with the origin O and the radius R, whatever, we don't care as much about the radius here. And then consider a line that passes through, that passes through the point P. And it is perpendicular, we want this to be perpendicular to the radius that's passing through OP. Okay, then this is called a tangent line. See, this tangent line to the circle intersects the circle as only 1 point. Okay, it's that's it. So that's why we call it tangent line. All right, so okay, for this tangent line, the question is, how are we going to find the slope of, let me write the question, the goal here now changes. Okay, our goal changes to, just a sec. Okay, so our main goal, you remember we were interested in instantaneous velocity or speed, right? Actually, it is this instantaneous speed is actually related to the tangent line. Okay, so we are still trying to answer that question. I just told you that you just make a table and look at the value, and actually the instantaneous speed is going to be close to that value. Okay, that's what we said. We didn't really say it's exactly that, but now we are going to show actually the instantaneous velocity at a point is going to be related to the slope of a tangent line. Okay, you're going to see that these guys are all related. This actually in ancient times, that's how they came up. Okay, they had to think, and they thought, and they reasoned it, and then they came up with this tangent line, the formulation, etc. And I mean, very important at that time. Okay, on those years it was very important, and still very important, because it's a main facts of calculus that we use every day. Okay, so let me tell you before I leave, because we have 4 minutes. I have to tell you the relationship secant line and tangent line. Okay, secant line, as we said, these are secant lines you can consider as the slope of the average rate of change, right? So see, if you go back, average rate of change. Okay, the average rate of change, we would say these are the slopes of the secant lines. Okay, let's look at let's consider a curve. Let's say I'm interested in the speed at P, at the point P. Okay, so what I'm going to do, I'm going to look at the average rate of speed, average speeds, okay, at that point, and then at this point, between these 2 points, I should say, and then with these 2 points, etc. I'm just getting all these average velocities, and each time I'm getting closer and closer to the real point that I'm interested in, and then these average speeds, okay, I look at where they approach to, and the point that they approach to is going to be the actually instantaneous speed at the point P. All right, which is going to be the same as, actually, it's going to be the slope of the tangent line. But why is that? So let's see why is it the slope of the tangent line. Okay, so forget about the average velocity, forget about anything I said. Just concentrate on looking at the secant lines and the tangent line. Okay, so what I'm going to do is, I'm interested in the slope of the tangent line. Just remember this, I'm interested in finding the slope of the tangent line. But let's say I only know how to find the slope of the secant lines. Okay, I only know, let me write it down very quickly. Okay, let's see. Okay, say I only know the slopes of this. Okay, sorry. Okay, say I only know how to calculate, how to find. I only know the slopes, not how to, but I don't know the slopes of secant lines. Okay. These secant lines are the lines written here. Look at the secant lines; they are getting closer to the tangent line. Look at that. This secant line is a little bit far away than this red tangent line, but this blue is getting closer to it. This blue is getting closer to it, and this blue is the closest of them all. Okay. So when you get close to that, each time the point that the secant line intersects the graph is different. It was intersecting at Q, now it's this intersecting at Q1, it's intersecting at Q2, Q3, and these Q points are getting closer and closer to the P. Okay, so and you should observe that these secant lines are, the slope of the secant lines are getting closer to the slope of the tangent line, right? Look, slope of this is very much similar to the slope of this red line, but this slope of this is not as similar to this one. Okay, as you get close to the tangent line, the slopes of the secant lines are getting closer to the slope of the tangent line as well. I want you to observe that. Okay, observe that. Slopes of the secant lines, okay, are getting closer to, I mean, as in terms of values, Okay, getting closer to the slope of the tangent line. Okay, this is obvious because look at the slope. I mean, how they stand. Okay, you know what the slope is, right? So the value delta y over delta x, you always look at the delta y over delta x. So this is very close to the value of this, okay, in terms of slope. Okay. Okay, so let's get this picture here. You can also see it in different perspective as well. This Q, instead of Q coming from the right, you can see Q coming from the left as well. Okay, so still the secant lines that you have are going to get close to the slopes of the secant lines are getting close to the slope of the tangent line here. It's the same tangent line, but you are forming the secant lines from the left and from the right. Okay, okay. So the tangent line to the curve at P is the line through P whose slope is the limit of the secant line slopes as Q approaches to P from either side. That's what we can say. Okay, so the slopes that you're going to find for the secants, look at those values and where they approach to, and they will approach to the slope of the tangent line, nothing else. Okay, not to another value. They are going to get very close to the slope of the tangent line. So this is very similar to building the table like that, because we built the table, if you remember here. Okay, you can consider these average speeds things as the slopes of the secant lines. Slope of the secant line, slope of the secant line, slope of the secant line here, and they are getting closer and closer to this 32, and in this case slope of the tangent line is 32. Okay, at that point you can see it like that. Okay, so I think that's the story of the speed and secant lines and tangent lines. Okay, that's the story. We will come back to it, but there's a relationship with all these things, and graphically, geometrically, they are related. And we will afterwards, next class, we will talk more about this picture, and you'll understand better. Okay. So this so far that's all to it. Do you have any questions you may ask?
No.
Okay, I'll say bye for now, and I'll see you next time. Okay, thank you. Bye-bye.